So there we are. And I'm just going to wait for you to type your question. Okay, what's the confusion? Well, never mind. Let's open up the essay, okay? So I'm going to change my share to the web browser. So can you see launch meeting now on your screen? So can you see launch meeting here on your screen? You just give me a yes if that's true, okay? So now you should see the homework for module 2. And now you should see the screen's flipping around like crazy. And here we have, we want to go back, I best guess, to module 1. And we have the science lab. So I'm going to link to that. Okay. So what you're supposed to do is you're supposed to go to this Understanding Science, read section 5 and read section 8. So if we go to Understanding Science, do you see if we scroll down here, section 5, the social side of science, a human and community endeavor. So you link here and you read all of this section here. And when we scroll down, do you see the little next? You keep going until you're done with section 5.
Okay.
So when we continue, let's see what happens eventually. I'm curious whether it says section 6. So I'm just going to keep going. I do know that if you keep pushing next, eventually you're going to go to section 6, and it keeps going on, and then you go to 7 and then 8. But I just want to see whether or not we will get to section 6 and know that we're doing that. Okay, I don't see section 6 yet, so maybe we already are in section 6. So what I'm going to do is I'm going to go back to contents here and see that section 5 ends when Science and Society starts. So when Science and Society starts, we're done reading section 5. And then I want you to read section 8, A Scientific Approach to Life. And as you can see, section 8 is the end of it, and it ends with summing up the science toolkit. So I want you to read this. And now I'm going to go back to the lab. And after reading those sections, I want you to address this issue here. I found on the internet that about 35% of Americans are unsure about the reliability of science. 1/3 of Americans, more than a third. I want you to write a persuasive essay. That means you're going to try to persuade me, convince me that science is reliable. And you also have to address the following idea that you do not have to be a scientist to what do I say there? I'm moving things around. You don't have to, where does it say? You don't have to be a scientist to be able to figure out if the science is reliable. So here, the idea is that this is a fairly open topic for you to give your ideas about from reading the discussion. So you might say, well, you know, one of the ways we might be able, we might want to believe science. So you're going to address that. How do we know that science is reliable, or why do we have faith in it? I'm using my fingers like this because faith is when you believe something and you don't really have a reason other than that. Maybe your parents told you. So maybe you guys have faith that there is the tooth fairy and they're going to leave you a quarter for every tooth you lose. And so, there's nothing written anywhere that says the tooth fairy is going to leave you a quarter for your tooth. Nowhere. So why do you have faith that you're going to get something from the tooth fairy when you're a little kid? So faith is when you believe in something just because you have it. There's no real reason. But why should we believe that science is reliable? In other words, why should you trust science? And I think the readings should inform you on why we should trust science. And then furthermore, I want you to think about this idea that how would the common person who doesn't take any science classes, how might they be able to trust the science? What can they do to inform themselves? And that's the idea of the essay. I want it to be about 1,000 words, and to give you an idea of how many words there are, what I wrote right there is 224 words. If you wrote that 4 times, that would be your essay. You'll see the submitting is a text entry box. So do you see this little pair of glasses here? I'm going to go to the student view. And this is what you see. And after you've written your essay, you're going to go to submit assignment. And you'll notice it says text entry. Copy and paste or type your submission right here. So if you've written your assignment as a Word document, you can just type it in right here. That's what I'd like you to do. And actually, I should say, if you've already written it in Word, you can copy all of the text and paste it right into here. Now, if you have done something different, for instance, maybe you wrote it out on a piece of paper in handwriting because your handwriting is very neat and you took a photo of that, you could go here to insert and you could insert a document and upload a document. Actually, when I think about it, the upload the document would be like a PDF or something of your paper that you've written. For most people these days, it's just far easier for them to type these things on their computer than it is to print out by hand. So, China, does that help you to understand what I'm asking for? So that's a yes or no.
Yeah, it helps.
Yep.
Okay.
You can hear me, right?
I can hear you. And actually, I faintly heard China.
Okay. Well, okay. So are we allowed to use outside sources as well?
Yes, you can, but I want the words to be your own. I don't want you to lift something from somewhere else and just put it into your essay.
Yeah. Okay.
So it's
So we're
gotta
allowed to
be,
use quotes or no?
what's that?
Can we like quote them?
Yeah, you can quote them. So you could say, blah, blah, blah says, and then quote marks. But I don't want your 1,000 words to be, 200 words of quote.
All right. Okay.
Okay. I want it to be your ideas. And so after reading that stuff, and so you can refer to the documents you've read, your ideas of how maybe people can become informed. Here's one of my thoughts. Did you guys ever take a science class in high school?
Yeah.
Okay. Did you talk about the scientific method?
Mm-hmm.
Okay. Have you read those sections 5 and 8 yet?
Okay. So when I thought we were only supposed to read that specific part, but not the others.
Yeah, only 5 and 8. So when you read 5 and 8, I'm going to switch my screen. And can you see the sections in 5 here?
Yeah.
So it talks about scientific community, science, a community enterprise, scrutiny, great expectations, misconduct. lying with science, not getting away with it, and then summing up those ideas. If you read section 5, it basically says that science has a way of checking itself because we don't allow scientists to really work on their own. We have people vet their ideas, and really before you print anything, you vet it, and you vet it to the community. And who is the community who's looking at your science? Well, it's not me who doesn't understand your science. It's an expert in the field who may or may not know you. And that's how you not get away with it is, you basically, whatever you do, it has to be repeatable. People have to look at it who are experts. And so you can't get away with it because there's too many people involved. It's kind of like in a family. If you have a large family, you're not going to have any secrets. You're not going to get away with anything because people will call you on it. Does that make sense?
Yeah.
So, that's kind of to me why you trust science. And if you take a look at 8, they talk a little bit more about, when you're looking at the media and so forth. And if you just look at the sections here, can you see that they're talking about, where do you get the information from? Like the first part, media. Second one, where's the information from? You skip down and you go, getting to the source. Convince me. How strong is the evidence? When you read these sections, you're going to find out that, we need to talk about what is the source of the information. Is it Tony who is just spouting something without offering any evidence? Or is it Dr. Fauci who's a specialist in transmissible or in viruses, telling you, well, here's what we can expect for COVID-19. I mean, are you going to believe him or me when I say, COVID-19 is nothing? And I'm a chemist, I should know. So, this section really speaks to the idea that when we look at that information, when you are looking at it, you're not supposed to trust me just because I teach chemistry. If I'm talking about chemistry ideas and I can back it up, then you might trust me. But you want to, trust the experts. Does that make any sense? But, the second part of my question was, well, how do we get people to understand this? That it is their responsibility to look into the source. How do you get that to happen? So that's the question. That's one of the questions I'm kind of posing to you. And maybe your idea is that just like we make people get a driver's license, maybe we get them a common sense license. You have to pass this course to be able to make decisions and maybe vote, because we want you to have an informed vote, not a opinionated vote from someone who has no business giving you their opinion. So does that help you at all with what you're supposed to write? So it's almost like you're given free rein to throw your ideas out there. You don't have to quote anyone else and say, well, the Public Institute at Berkeley says that we should blah, blah, blah. I want to know what you think. So it's a pretty open topic here. And as such, I'm going to be open to the ideas that you have.
Okay, that makes sense.
Okay. So it's supposed to be actually a low key thing that makes you think about, well, if I were in charge, what recommendations would I make? And when I say recommendations, of course, when someone's in charge, they rarely make it happen. They listen to ideas and they say, okay, so we're going to try this. That's the way it normally works. Fair enough? Are we good to go? All righty. Are there other questions that you would like for me to address? Okay, well, if you don't have any, I'm going to go ahead and we're going to look at some problems from the book. So I'm going to change my share so that you're going to be looking at my tabletop in just a moment, okay? And am I recording this? Yep, I'm recording this. The reason I'm checking is because yesterday I forgot to record the afternoon session. And I can't go back in time and record it. Okay, can you see? There we go. Can you see these problems here? Give the formula and number of each ion that makes up each of the following compounds. Let me show you how to do this. And I'm gonna, before I get started on this, I wanna bring out my book here and show you the table of contents here. So the table of contents by chapter, you can see we're in chapter 2, atoms, molecules, and ions. If you flip the page one more, you'll actually see a more developed table of contents for each chapter. And here's where chapter 2 begins. So we've already done atomic structure, atomic number, atomic mass. We've already looked at isotopes and atomic weight. We've already looked at the periodic table. We've looked at molecules, compounds, and formulas. And yesterday we did ionic compounds, formulas, names, and properties. And actually the day before we actually looked at atoms and molar mass. So really we have 2 more sections to do, and that's chemical analysis, determining compound formulas, and instrumental analysis, determining compound formulas using mass spectrometry. And we've done a little bit of 2.8 already. And we've done a little bit of 2.6, but we're going to spend a more time on 2.6. And Monday, we're going to be spending a whole lot of time on 2.7. And then we're done with the chapter after Monday. So are you aware of where we're going in the future here? We good? So today we're going to do some more stuff with the atoms in the mole, but we'll also do some stuff here with ionic compounds. So our job here, our task here is to figure out what the ions are. The first thing you're going to do when you look at this is you're going to say, oh, there's a metal in each one of these. And then I also have nonmetals. So you're going to say it's ionic. Now, the question tells you it's probably ionic because it says ion, right? But if it had not said ion in there, we'd still know these are ionic because metal, non-metal. Are you okay with that? Okay, excellent. Now, for us, we're going to make it really simple. The first metal you see is the cation. So what's the cation here? It's Mg. What's the cation here? It's aluminum. What's the cation here? It's copper and titanium and potassium and calcium. So looking at these, some of these we should know the charge. Which ones should we know the charge on? I'm going to draw a quick periodic table here. Now, these are the metalloids. And this is a nonmetal. And these are nonmetals. And the rest of these are metals. So all of these nonmetals are going to form anions, and you should know the charge on them. And the charge is really easy to figure out. If it's a nonmetal, the charge is 0 if it's in 8A, -1 in 7A, -2 in 6A, -3 in 5A, -4 in 4A, and then here, this is boron. And here, what do we have next to carbon? We have carbon, I forget. Well, boron, carbon, nitrogen. I guess I got all of them. So here, this is going to have no charge on it because it turns out that metalloids don't usually form ions. Metals form ions. If it's in group 1A, you should know it's a +1. If it's in 2A, you should know it's a +2. If it's in 3A, you should know it's a +3. And if it's here and it's zinc, you should know it's a +2, and you should know silver is a +1. So all of these elements here that I'm going to highlight in green, including these guys here, you should know the charge just because of where it is in the periodic table. Are you okay with that? Okay. So what are the ones where you have to figure out the charge based on the formula of the compound? That's the rest of these in purple. You have to figure out the charge based on the compound. So going back to this, do you see how magnesium is in group 2A? So its charge is +2. That's a given. Aluminum is in group 3A, so it's a +3. Copper is a purple area, so we have to figure out the charge. Titanium is a purple area, so we have to figure out the charge. Potassium is 1A, so that's a +1 automatically. Calcium is in 2A, so it's a +2 automatically. And you want to be as quick as I am about it. You kind of want to know where these elements are on the periodic table so that you don't have to spend too much time looking for it and then figuring out the charge. So here, the first metal is going to be a cation. Now, what is the rest of it? The rest of it is the anion. So for magnesium, the rest of it is CH3CO2, but there's two of them. You see that little two? There's two of them. So if there's two of them, and we know that the formula has to be neutral and the simplest ratio of ions, what does the charge on each one of these have to be if that's a +2, and these two charges have to add to that to get 0? -1 each. So that's how you figure out the formula or figure out the ions in the formula. So what do we have here in aluminum? What's the anion? It's OH, and there's 3 of them. What is the charge on each one to make this work? It's got to be a -1. In C, what is the anion? Well, we've done copper, so the rest of it is the anion. So this is one where you need to memorize the charge on this one, because the charge of copper depends on the charge of this one. Now that we've memorized that charge, what does the charge on copper have to be? Has to be +2. So we're not going to do the rest of these, but this is how you would figure out the formulas of the ions. So to summarize, the first metal is the cation. Everything else is the anion. So here, I'm going to write out 2 formulas. And I want you to write out the formulas of the ions. When you're done, just give me a little check. Okay, so the rule is the first metal you run into is the cation. So we've got a cation made out of K, which we know is +1 because it's in group 1A. What is the rest of this? It's the anion. Okay, so what does the charge on this one anion have to be? -1. Here, what is the cation? It's sodium. But the 2 means that there's 2 of them. So what is the anion? It's the rest of this. What does the charge on this have to be if you have 2 plus 1s? And the answer is -2. And that's how you figure out those ions in that formula, in those formulas. The first metal is the cation, the rest is an anion. What do we call an anion made out of 2 or more elements? This is called a polyatomic ion. What's this one called? Oh, excuse me. I just gave you the answer. This one's called a polyatomic ion. This one's a monoatomic ion. And so this is actually a monatomic ion, but there's 2 of the single atom ions, 2 of them. Okay? All right. So let's move on from there. This is a problem that you should be able to do fairly easily. Platinum is a transition element and it forms platinum plus 2. Write the formulas for the compounds with chloride ions. So chloride is in 7A, so it's a -1. So we do the switch and simplify. PT1, Cl2, and there's one of the compounds. And if you have platinum 4 and sulfide -2, you do the switch. And this can be simplified to that. Oh, why am I writing chlorine here? Should be that, which simplifies to that. So that's 46. Any questions there? Or are we good to go? Okay, you got a yes, but you've had that yes there for a while. I'm just going to assume you're still good to go. Okay, which are correct formulas for the following ionic compounds? For those that are not, give the correct formula. Can you see that calcium is a +2 because it's in 2A, and oxygen is a -2 because it's in group 8, 6A? Is this a correct formula? No. Why is it not correct? It doesn't add up to 0. So what would be a correct formula? And the answer is 1 of each, because that adds up to 0, and you get that. You could also say that the correct formula could be 2 of each. If we had 2 of each, we would get Ca2O2, and that's not correct because it can be simplified. Are we okay on A? Now I'm going to let you do B, C, and D on your own to see if they make sense, okay? Okay, name each of the following compounds. So to name them, you have to first identify the ions. So remember our identification of the ions. The first metal is the cation. So the cation here is calcium with a +2 because it's in group 2A. So here we have 2 acetates. This is also the formula for acetate ion. And this is calcium ion. And notice there's no number after calcium because it's one of those ions where it's always a +2, so you don't need to write calcium 2. You put the names together and you get calcium acetate. So notice in the formal name, does it say ion? No. Well, how do you know it's ionic? Well, because it's got a metal plus it's got another ion. We know that's an ion. So if that's an ion, that's got to be an ion. It's ionic. For B, can you see that we have 3 nickels? And we have 2 PO4s. So how are we going to do this one? You have to memorize that these are -3. And the total charge is -6. So the total charge here has to be +6. So these are each +2. And this is nickel 2 ion. This is phosphate. Put it together and you get nickel 2 phosphate. All right, I'll let you do C and D on your own. Or do you understand how we went about A and B? Okay. So give the formula for each of the following compounds. This one shouldn't be too bad, right? Because just like ionic compounds, if the first element, the first metal is the cation, here the first name is the cation. So what's a calcium cation? Ca2+. What's a hydrogen carbonate? HCO3 -1. So we do the switch and simplify. This 2 goes here and this 1 goes here. So it becomes calcium, HCO3, and we put a 2 there. And what's wrong with this is that this 2 looks like 32 oxygens. So to make this work, we put parentheses around the polyatomic ion. And this is calcium hydrogen carbonate. Are we okay with that one? Okay, then let's look at magnesium perchlorate. Here's magnesium. Here's perchlorate. So what is the formula? Tell me when you're done. Okay, so you should get Mg parentheses MnO4 2. Any questions about that one? Okay, then let's move on. You can do the rest of these yourself. Now we have right formulas for the 4 ionic compounds that can be made by combining these. So we want to combine magnesium with phosphate, magnesium with nitrate, iron 3 with phosphate, and iron 3 with nitrate. So we're going to do the switch and simplify. And, you know, that's pretty straightforward. So we're going to skip this one. Consider the 2 ionic compounds, sodium chloride and calcium oxide, in which compound are cation, anion attractive forces stronger? Explain your answer. So this is a formula you don't need to memorize, but you need to understand. So F is the force of attraction. And because it's an attractive force, the value is going to be negative. K is a constant. And it doesn't matter what the 2 ions are, it's always the same. N plus is the charge on the cation. And notice I did the absolute value. N minus is the charge on the anion, absolute value. E minus is the charge on an electron. And we actually use a value of negative blah, 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 blah coulombs. And it's a negative value because the charge on an electron is negative. D is the distance between the nuclei. Now here, for every ionic compound, the charge on an electron is the same. The amount of K is the same. The only thing that will differ between two compounds is the charge on each ion and the distance between the nuclei. Let's look at the distance between the nuclei now. So if we have a calcium atom with a +2 charge, and then we have an oxide with a -2 charge. This is the nucleus, and this is the nucleus, and this is the distance between the nuclei. That corresponds to the D. You can see that this D is equal to the radius of calcium plus the radius of the oxygen ion. So can you see how this distance are the two radii summed together? Okay. Now, it turns out that when we look at calcium versus sodium, sodium is actually smaller than calcium. And when we look at chloride compared to oxygen, chloride is actually bigger than oxygen. And so in this particular case, when you look at the distance between the nuclei, my chloride is not big enough, is it? I need to make it bigger. There, okay. So when you look at the distance between the nuclei, they're roughly the same. They're roughly the same. How would you know that sodium is smaller than calcium? And how would you know that chloride is bigger than oxygen? I'm going to show you that. So if we look at period 2, we've got lithium, which is going to be a +1. We've got beryllium, which will be a +2. We skip a bunch. You've got boron, which doesn't form an ion. Carbon, which is a -4. Nitrogen, which is a -3. Oxygen, which is a -2. Fluorine, which is a -1. Now, there are trends for the sizes of these ions, but roughly speaking, these have the same radius. They're within 10% of one another. And these have the same radius. But these do not equal these. These, because they've lost electrons to make them positive, they're actually smaller than the actual neutral atom. These, because they have electrons added onto them, they're bigger than the neutral atom. But these are roughly the same radius, okay? Now, when we look at calcium, calcium is right here. And when we look at calcium compared to beryllium, calcium is larger. So here would be a calcium ion, and this would be a beryllium ion. So the further down you go in a period, the larger they are. So if they're in the same period, the cations are roughly the same size, the anions are roughly the same size. If they're in a different period, the lower period is larger. So let's see how we figure out what's going on with these guys. So I'm going to have to draw a periodic table. Here's sodium. Here's magnesium. Here's calcium. If we go across, we see chlorine. And if we go up, here's oxygen. So we want to make comparison of these, and we can see that sodium is going to be smaller than calcium because they're in different periods. Period 3 is going to be bigger than sodium. If we look over here, we can see that chloride is going to be bigger than oxygen. Okay. Now we're looking at the compound sodium chloride versus calcium oxide. And we know that sodium is smaller than calcium. So this is the small and this is the big. And for chloride and oxide, we know that this is the big and this is the small. So can you see we've got a small and a big combined with a small and a big? That means that roughly speaking, D is roughly the same. And I want you to recall that D is the distance between the two nuclei. Okay, so that's going to be important. When you look at the charge of sodium is less than the charge of calcium. So +1 is less than +2. And here, when you look at the oxygen charge is bigger than the chloride charge. And we're looking at the absolute value of the charge. 2 is greater than 1. So how do we apply all this information? Well, let's take a look at that formula again. F is negative K N plus E minus N minus E plus, or E minus, all over D squared. We don't care about K, E, and E because they're the same for any ionic compound, but we can say this: the force of attraction is proportional to the value of the positive charge. It's proportional to the value of the negative charge, and it's proportional to 1 over the distance squared. So that means larger N plus, greater force. So I'm going to ask if you understand this first part right here. The larger the N, the greater the force. So what would we put down here for the negative charge? Larger negative charge, greater the force. What would we put down here? We would put larger D, smaller force. So you learned in algebra that when you have something in the numerator and you're comparing it to something where it's 1 over the denominator, bigger denominator, smaller number. Are we okay with this one? Larger D, smaller force? Okay. So when we compare calcium oxide to sodium chloride, wouldn't you say that these have larger N plus and N minus? So, and these have smaller? So we would expect the force to be larger over here, but we have to compare the D's. Now for the D's, we know that sodium is smaller than calcium. So here's a small sodium, here's a bigger calcium. We know that chloride is bigger than oxygen, so here's a big chloride, and here's a small oxygen. So when we look at this distance here, it's roughly the same. So we'd say about the same D for each of them. So overall, you'd have to say, well, the D doesn't matter because it's about the same. So calcium oxide has the greater force of attraction. So any questions about how we decided on this? Now, how would you write that answer out on the test? And the answer would be, you have to look at all of these things. I would start my answer with this. The force is equal to negative K n plus E minus n minus E plus over d squared. And then I would say that the force is proportional to n plus and the force is proportional to n minus. So this would make CO greater force. And we would convince people by saying CO is 2 plus, O is 2 minus, Na is plus, and Cl is minus. So we can see that. And we would say that the distance between ions is about the same because, and here this should be between the nuclei, because calcium is bigger than sodium and oxygen is smaller than chloride. So that means here you've got a big, small, and here you've got a small, big. So they should kind of balance out. And then you would say, so CaO should have a greater force of attraction. So this is how you would explain this. Now, you could write sentences for all of this, correct? But if you're asked for an explanation and you give these bullet points, this is pretty easy to follow. So this would be a great explanation, in my opinion. Pretty easy to follow. The only thing that could make it better is say D is da-da-da, is about the same, so does not matter. Are you okay with this explanation? Okay, nice little bullet points. Okay, let's put that one off to the side. Here we've done plenty of these, and we've done plenty of these. We use the molar mass ID just to remind you of the molar mass. If we have platinum, and platinum has a atomic number of 78 and a number here of 195.08, we know that this means that 1 mole of platinum is equal to 195.08 grams. So if we are given 0.063 mole of platinum, we can multiply by 195.08 grams of platinum over 1 mole of platinum, and we can get the grams of platinum. Now, I always like to estimate, and this number is not 0.63. It's not. 0.63 is too big, but I'm going to pretend it's 0.63 because 0.63 is roughly 2/3. So what is roughly 2/3 of 195? Well, it's roughly 130. So if this were 2/3 of this, we'd have 130. But this isn't 2/3, it's 1/10 of 2/3. So what's 1/10 of my estimate of 130? 13. So I think the answer here should be about 13. Let's take out our calculator and do the work. Where is my calculator? $195.08 times 0.063, and I get 12. My estimate was 13, I got 12. There's your answer. Only two significant figures because leading zeros don't count, but the 6 does and the 3 does. So 12 grams of platinum. Any questions there? Okay, well, what if we had 102 grams of platinum? How do we figure out the moles? And the answer is you use the same thing up here, only you put the 195 grams on the bottom, and I'm going to put platinum and 1 mole of platinum on top. And can you see that roughly this is half of that? So our answer should come out to be about 0.5. A little bit more because this is a little bit more than half. So that would be how many moles of platinum you have. A little bit more than half. 3 significant figures because of this 102. Are you guys okay with that? Okay, let's move on. Calculate the amount of moles represented by the following. We've already done something like that, so we're going to skip that. And now we're asked, you are given 0.1 gram samples of potassium, molybdenum, chromium, and aluminum. List the samples in order of the amount from smallest to largest. So if we look at our periodic table, here's potassium, and it's got the number 39.10. Molybdenum is over here, and it's 95.96. Chromium is above, and it actually should be in the same row as potassium. And then aluminum is over here and up a little bit, and it's 26.98. So we have the same mass of each. So one way to do this problem is the following. 0.10 grams of potassium times 1 mole of potassium over 39.10 grams of potassium, and we get a number here. 0.1 divided by 39.10, and this should come out to be a pretty small number. So I get 0.0026. So what would we do for the rest of these amounts if you have 0.10 grams of each? We would do 4 calculations. Does that make sense? Are we good with that? Let me show you another way to do that. I'm going to call this guy a tangerine. I'm going to call this guy an orange. And the reason I'm doing that is because tangerines are smaller than oranges, right? Just like aluminums are smaller than potassium. Are you good with that? What's a little bit bigger than an orange? Grapefruit. So I'm going to call my chromium a grapefruit, okay? And what's a little bit bigger than a grapefruit? Maybe a melon? Not a watermelon, but maybe like a honeydew melon or something like that. That's bigger than a grapefruit, right? So here we have these comparisons. I want you to imagine if I had 10 pounds of tangerines, 10 pounds of oranges, and 10 pounds of grapefruit, and 10 pounds of melon, and I wanted to know the number of each. How many tangerines might you get in 10 pounds? Shoot, you might get 20 tangerines. How many oranges might you get in 10 pounds? You might get 10 oranges. Why do you get fewer oranges in 10 pounds? Because oranges are bigger. Does that make sense? And here you might get 5 of these, and with a 10-pound melon, you might get 2. So you could say, if we're going to go from smallest to biggest, smallest amount to biggest amount, you're going to say molybdenum is going to be the smallest, chromium the next smallest, then potassium the next smallest, and then aluminum the next smallest, but you'd want to explain why. And you'd say simply this: the amount is proportional to 1 over the mass. So larger mass, fewer moles. And then you would go on and say, for molybdenum, 95.96 is greater than chromium, which is 52.00, which is greater than potassium, which is 39.10, which is greater than aluminum, 26.98. Notice, since these are opposites, if the amounts get smaller, the numbers of atoms gets bigger. Are you with me there? So I've given you 2 ways of doing this problem. You could kind of explain it, or you could do 4 calculations, look at the numbers, and then say, okay, this is what we have more of. Are we clear on that there's a couple of ways to do this? Okay, then let's move on. Okay, a semiconducting material is composed of 52 grams of gallium, 9.5 grams of aluminum, and 112 grams of arsenic. Which has the largest number of atoms in this material? Now, for this problem here, we don't have the same mass of each, so we can't just look at the amount, the molar mass of each. So we take our 52 grams of gallium, multiply by 1 mole of gallium, and the molar mass of gallium is 69.72 grams. And if we stop here, this is what we get. Well, you know what? I don't want to calculate it. I'm just going to say about, let's see, 52 out of 70. Wouldn't that be about 0.8 mole? Roughly? Because it's like 5 over 7. Maybe it's more like 0.7 mole. Okay, next one, we have 9.5 grams of aluminum times 1 mole of aluminum over 26.98 grams of aluminum. And wouldn't you agree that this is about, this is like 10 over 26? So roughly 10 will go into that 2.5 times. So this is roughly, I want to say 1/4, but I think it's maybe a little more than that, but I'm going to say 1/4. Actually, I'm going to say 1/3. So I'm going to call it around 0.3. And lastly, we have 112 grams of arsenic times 1 mole of arsenic over 74.92 grams of arsenic. And can you see that's going to go in there 1 time plus a leftover of 35. So this is going to be about 1.5 mole of arsenic. So do you understand? I didn't bother using my calculator. I just said, this is about how much we have. Let's use our calculators and see what we actually get now. 52 divided by 69.72 is 0.75. 9.5 divided by 26.98 is 0.35. And 112 divided by 74.92 is 1.5 or 1.49 if we round off to three significant figures. So do you see my abouts are close to the real amounts? Now let's go back to the problem. It says, which has the largest number of atoms? And I did not calculate how many atoms. I did not. But if you were comparing 0.7 dozen to 0.5 dozen to 1.5 dozen, which has more eggs? Even though this doesn't tell you how many eggs, which has more eggs? This one, because 1.5 dozen is more than 0.7 or 0.5. Which has the least amount of eggs? This one. And which one's in between? The middle. So what I'm trying to point out to you is I don't actually have to count how many atoms there are. I can look at moles of atoms. So we're supposed to go, which element has the largest number of atoms in this material? Arsenic. Arsenic, because it has more moles of atoms. So do you understand that this would be fine for this example? We aren't even asked for how many atoms. We're just asked which has more. And this does it. Are you guys okay with that? Okay. Okay, calculate the molar mass of each of the following. If this were a question on the test, here's how I'd want you to work it out. So we're going to do this for iron 2 gluconate. So first of all, I'd say there's 1 iron. Then I would say that there's 6 carbon in parentheses, but since I have 2 of what's in parentheses, I actually have 12 carbons. How many hydrogens? Well, 11 in parentheses, but I have 2 of what's in parentheses, so we have 22. How many oxygens? 14. So, do you understand where I got these numbers from? This is the number of atoms. You okay with that? Okay, now let's look at the molar mass of each of these. Iron is 55.85. Carbon is 12.01. Hydrogen is 1.01. Oxygen is 16.00. And we want to multiply each of these together. So we have 8.85 grams of iron in our 1 mole of iron 2 gluconate. We got 144.12 grams of carbon in iron 2 gluconate. Now, what do these arrows indicate? They indicate where I would round to if we were done. 4 zig figs, exact, because we counted them. So you get 4 zig figs. Over here, we have 22.22 grams. So this is good to hear. And here we'd have, let's see, 16 times 10 is 160. 16 times 4 is 64. 64 plus 160 is 224. And that's good to hear. When we add these all together, we get 5, 6, 7, 8, 9. Nothing to carry. 8, 9, 10, 11. Carry the 1. 10, 6. Carry the 1. 10, 4. Carry the 1. And we get 4. And we round to right here, so 446.2 grams. And we would say for the final answer, 1 mole of iron gluconate is equal to 446.2 grams of iron gluconate. And that'd be our final answer. So I want to see this work right here. Any questions on how to get the molar mass? Let's go ahead and check and see if our answer is correct. So I'm going to go here to my web browser, and I'm going to go to iron 2 gluconate molar mass. And look at what they have, 448.156 grams, and we got 446. What is our source of 448 here? It doesn't say. Let's scroll down. Do you see this one that says Pub Chem, NCBI, NLM, NIH, GOV? Well, I know this is a government site, and I know that NIH is the National Institute of Health. And look at their molar mass, 446. Does that match ours better? Absolutely. Who am I going to believe? This one who has no source above, or this one that has a gov source below? I'm going to go with the gov. This one below also says 446, and it says Chem Spider. Should I trust Chem Spider? That sounds like someone in their garage who likes chemistry and Spider-Man put it all together, and they said, oh, Chem Spider. I don't know if I'm going to trust that. American Elements, that seems more trustworthy because it's American and it says elements, but I don't know. Wikipedia actually ends up being pretty trustworthy, but you know, it's one of those open source things where anyone can write anything they want. Now look at this one here. This says sigmaaldrich.com catalog. What does this mean? It means they sell this stuff. They sell it. So I might believe this site a little bit more than anyone else, or than some of those other ones. So this is one of those things that I was talking about with your essay. What kind of source are you going to believe? To me, it's an unreferenced source. They might be right, but I don't know if I would bet my bippy on it. Okay, so do you understand the work here? You good? Okay, let's take a look at this next one. Calculate the molar mass of each hydrated compound. So for this, we need to know how many atoms are in each of these. So if we look at this first one, how many hydrogen atoms? And the answer is 6. Because the different way of writing this is this way. That's what that 2 means, 2 H2Os. I think perhaps a better way to write this would have been this, but they don't do that. For hydrates, they write it as a dot and the number of H2Os. So here, 6 hydrogens. How many carbons? 2. How many oxygens? 4 plus 2 more, 6. So then we would multiply this by 1.01 grams times 12.01 grams and times 16.01 or 0 grams. And we go from there. Any questions about that? Okay, so we're not going to finish that one off, but here's another hydrate. And that does say 1/2. And it kind of tells you why we don't do this. This does not make sense. And it doesn't make sense. How many calciums? 1. How many sulfurs? 1. How many oxygens? 4.5. And this is exact. How many hydrogens? 1. So we would calculate the molar mass based on this. Let me explain to you what this really means. What this really means that if you have 2 calcium sulfates, you have 1 water. It's a ratio of 2 to 1 or 1 to 1/2. This is what this really means. So you might ask, well, why don't you write it this way? If it really means that, why don't you write 2 of these and 1 of those? And the answer is because this means that 2 of those and 2 of those. So that's why we put the 1/2 in the middle of the formula. Okay, so we're not going to calculate that molar mass. 111 is refer to the book. We're going to finish here with 76. How many ammonium ions and how many sulfate ions are present in 0.2 mole sample? So when they say how many, they don't want to know how many moles. They want to know how many ions. So to do this problem, you have to understand that 1 ammonium sulfate is equal to 2 ammonium ions, and it's also equal to 1 sulfate ion. So this is the product, if you will, and this is what you make it out of. So it's almost like a recipe that we're deconstructing. This is made out of 2 of those and 1 of those. Are you okay with that? Now, we can also say if we have 1 mole of NH4, 2 SO4, that means you would make that out of 2 moles of ammonium ions. And we don't usually write that. And 1 mole of sulfate. Do you see it's the same ratio, but we just put mole in each one of them? And we also need to know that 1 mole is 6.022 times 10 to the 23rd. So let's see how we can get the number of ammonium ions in 0.2 mole of ammonium sulfate. So I'm going to take the 0.20 mole of ammonium sulfate. I'm going to use this conversion up here, right here, I should say, and turn that into moles of ammonium ion. And then I'm going to use this and turn that into ions. So here's how it looks. So that's the beginning. And then I'm going to write that we actually have for every 1 mole of ammonium ion, we have 6.022 times 10 to the 23rd ammonium ions. And when we do all the work here, we get 2.4 times 10 to the 23 ammonium ions. And that would be the kind of work I would expect to see for the calculation of ammonium ions. How would this change for the sulfate ion? Well, the answer is here we'd have 1 mole of sulfate to 1 mole of ammonium sulfate. And here the numbers would be the same, but it would say sulfate and sulfate instead. And if the only thing that changes is that the NH4 is changed to sulfate, this would end up being sulfate. And if that 2 were now a 1, we'd get 1.2 times 10 to the 23rd. We can do the same thing for the next part, which says how many atoms. So we could say 1 mole of NH4 to SO4 is equal to 2 mole of nitrogen, 8 mole of hydrogen, 1 mole of sulfur, and 4 mole of oxygen. So do you understand where these numbers came from? So if we asked how many moles of nitrogen, you would write 0.20 mole of NH4 to SO4 times 2 mole of nitrogen per 1 mole of ammonium sulfate times 6.022 times 10 to the 23rd nitrogens per 1 mole of nitrogen. And we would get the same number as this. (2.4 times 10 to the 3rd nitrogen. So this is how you could calculate the nitrogens. Or you could start from here. How many nitrogens in 1 NH4? 1. You could do that instead. So the deal here is you're supposed to be able to look at formulas and understand that the numbers here represent ratios of atoms or ratios of moles of atoms or ratios of moles of ions. However you want to look at it, so it helps you to do the problem. Okay? And that's it for today. Next time, we're going to be doing some problems where we figure out formulas and things like that. So thank you for attending. And do you have any last questions before we cut the feed? No questions? Okay, so you know the deal. At the end of every session, you're supposed to turn on your mic and say goodbye to everybody. So turn to your sibling and say goodbye. We'll see you later.